get going with a little bit of this stuff here. All right, rational exponents is where we're going to start. So rational, remember, just means fraction. Exponents is what we're going to be dealing with in this first section. And for whatever reason, my computer doesn't like this cable.
It's okay for like 3 minutes.
Yeah, I know. It was fine a while ago. Now it'll be okay. It doesn't really matter. Y'all can see in the rose-colored glasses. This is green shaded glasses. St. Patrick's Day coming up, so it'll be good way to get ready for it, I guess. All right, so we'll start with just simplifying. So start with an easy one. 49 to the 1/2 power. All right, so the 1/2 power is like it's a square root is really what it is. And the way that I try to simplify these things, if I'm going to do it by hand, and the reason I show you doing it manually without the calculator is because when you start doing this with variables, the calculator really doesn't help you any. So you've got to know what's happening there and why things are working the way they do. So when I think about the number 49, I know that it's 7 times 7. So it's really 7 squared to the 1/2 power. And then once you get the number simplified with a factor tree, you can then start using exponent rules. And exponent rules say that you multiply those exponents together. So we're going to multiply 1/2 times 2 and get 7 to the first power, or just plain old 7 out of that. With the graphing calculator, just simple, type in 49, and then you're using the caret symbol, which is right above the division symbol and right below the clear button. And you can type in that fraction, 1/2, and it'll crank out the 7 that it is. Now, that doesn't always work, to be a nice number, but we've got to be able to simplify it, whether it's a nice number or not. But really simple idea there with the graphing calculator. I'll do several more here. Let's do 64 to the 1/2 power. And I know a lot about 64. I know that it's actually 2 times 32. I know that 32 is 8 times 4, and 8 is 4 times 2, and those 4s turn into 2s. So that's 1, 2, 3, 4, 5, 6 2s, which is, multiply those together. 6 times 1/2 is 2 to the third power, which is 2 times 2 times 2, which is 8. Now, again, we can all type that into the calculator and get an answer spit out to us about that. But knowing what those exponents do is going to help us when we go to do our exponents later with variables. Yes, ma'am. You could. It doesn't matter what you start with here, and then and you could have done that with 8 and 8 and had 8 squared and done the same thing. It would work the same way there because of the number that it is. So you just want to break that number down. I always break it down as far as I can to where every end of my tree is a prime number. That way I don't miss anything there. But yes, you could have done with 8 and 8 just like we did with the 49 and the 7s. It would have been the same for this one just because it was that number. Let's look at a negative number like negative 144 to the 1/2. Got to be real careful on this because that negative is not with the 144, even though it looks like it is. This is really negative and then 144 to the 1/2. That's how it's understood as far as mathematically speaking. That negative happens last. Order of operations, please excuse my dear Aunt Sally, parentheses, exponents, then multiplication and division. That negative is like multiplying by -1. So we got to take care of that half exponent first. And you can break down the 144. If we take that same idea and just do the 12 and the 12, that would work. We have a negative and then 12 squared to the 1/2.
and then multiply those two fractions or two exponents together, it ends up being negative 12 as a final answer out of that. If you break down the 12s to 4 and 3s, you get the same thing happening there. You get the idea of what's going on here. Let's look at a different fraction exponent. And like I haven't moved this cable at all, it just changes color, so I understand. Oh well, whatever. Negative 27 in parentheses to the 1/3. So we do a 1/3 power instead of 1/2. So changing it up. So this is different than the 1/2 power just by what we multiply by at the end. So we're going to break down the 27. 9 and 3, 3 and 3. So we really have a negative and then 3 cubed raised to the 1/3 power. That's really what we have. And then we multiply these together. 1/3 of 3 is 1, and we have a negative 3 as a final answer there. So it just takes breaking down those numbers. And if you type that into the calculator, parentheses, negative 27, close the parentheses, raised to the 1/3, you're going to get that same result back. Okay, so it's really easy stuff here. Let's look at a something that's a little bit different on this. Would be like if we had a negative 64 to the 1/6 power. So we know about 64. We're dealing a 1/6 power instead of a 1/2. So this is where we've got to do the different numbers. Can't just do 8 and 8 because then we end up with another number to a fraction exponent. So if we do 64, if we did the 8 and 8, that's 8 squared. That's not going to cancel out with a 1/6 nicely. So I'm going to go ahead and break down the 8 into 4 and 2, 2 and 2, 4 and 2, 2 and 2. So that's 1, 2, 3, 4, 5, 6 2s. I'm going to split that negative off from it. Now here's where we run into issues with this because we have a negative to an what's called an even index. And the index that I'm talking about is the denominator of your fraction. Anytime you got a negative with an even index, the 2 to the 6th and the 1/6 power, that's going to be 2. But the negative gets that 1/6 power as well. And any negative to that is going to be a non-real answer. So this is a non-real number. And it's not necessarily a complex number. When we dealt with complex numbers, when we were solving quadratics and things, that had to be like the square root of -1, stuff like that. This is not a square root. It's a 6th root, which is a different ball game out of that. If you were to type that in your calculator, just like it is our negative 64, oops, I meant to put parentheses, negative 64, close the parentheses, raised to the 1/6 power. It should, notice how it's giving me this I mess here. It's giving me a big long decimal thing in front of there, so it doesn't simplify out the right way. So we're going to call that a non-real number. And the reason for that gets you there is the even denominator. Any kind, you got a negative inside of something and you got it raised to a fraction exponent or rational exponent with an even denominator, that's when you're going to have that non-real number out of that, which is a different thing. Now, the parentheses are very important there because if I go to my calc to work out negative and then 64 to the 1/6, that's a different problem. That's like negative and then 64 to the 1/6, like a separate problem. And then when I do that, that'd be 2 to the 6th power to the 1/6. And that actually is -2. If you go to the calculator and you just type in -64 raised to the 1/6 power. It's going to crank back the -2 out of that, but it's because the parentheses are not there. Parentheses are very, very important. Whether you have them or not, they make a difference on how these simplify out. So when there's parentheses in there, you're going to check them with the calculator. Make sure you type the parentheses in the same place that they are in the problem. Because if you don't, it is not the same. All right. So, and if it's a negative number inside of those parentheses and an even denominator, you know, that's not a real, that's not a real number that you're getting out of that. Let's look at something like this, 125 to the 1 power. Well, we know about 125. I know it's divisible by 5 because it ends with a 5. 5 and 25, and that's 5 and 5. So that's 5 to the 3rd power to the 1/3. Multiply the exponents. 5. Boom. All right. Let's put the negative in there in parentheses to the 1/3. This one we don't have to worry about so much because we've got the denominator of our rational exponent is an odd number. If it's an odd number, then the negative doesn't affect anything. It works out okay. So only do we have to worry about the negative when it is has an even denominator. Since that's odd, we don't have to worry about it. We just work it the same way. I'm going to treat this as -1 times 125, which we already know is 5 to the 3rd. So that's -1 times 5 to the 3rd to the 1/3. The rules for exponents are you're going to multiply both of those by that 1/3. So that's -1 to the 1/3 times 5. -1 to the 1/3 is -1. -5. So I'm working this out by hand, knowing that you can type this into the calculator and get it to simplify some of these things. But you've got to be careful about even denominators on your rational exponents if it's a negative number that you're working with there. Doesn't always cause a problem, only if it's an even denominator. That's the only time it causes a problem. Let's look at some improper or some different rational exponents. Don't have a numerator of a 1. Everything we've done so far has had a numerator of a 1. So let's look at something that has, I'm going to unplug it and try again, because that is really bugging me. Nope, no change. Okay. Let's do, I don't want to let it around. 81 to the 3/4 power. So a different numerator on that fraction. So when we go to do our work there, we're going to break down 81 as 9 and 9, 3 and 3, 3 and 3. So that's 3 to the 4th power to the 3/4. Multiplying those two together, 3/4 times 4 would be 3, which would be 27 when you work it out. And again, you can type that into your calculator, 81 raised to the 3/4, and it cranks that back out. The only time we got issue is if it's a negative number and an even denominator. That's where we got to watch out for things. Example J, let's do 25 to the 3/2 power. So a different, an improper fraction as an exponent. So that's 5 and 5, 5 squared to the 3/2. We're going to multiply the fractions together. 3/2 times 2 is 3. 5 cubed, we said earlier, is 125. And again, you can punch these in the calculator. It's going to give you back that solution, but you've got to be careful about what's going on there with the even denominators. Be careful with the negatives and the even denominators, and if you get non-real solutions. So be careful of non-real numbers. That only happens if you've got an even denominator out of that. Okay, let's look at doing a little bit more with operations like multiplying and dividing, those things. So what's the rule when you multiply like x cubed times x to the fifth? What do you do with the exponents? You add them together. It's x to the 3 plus 5. You get x to the 8th. Okay, we know that rule. What's the rule when you divide? You subtract them. So that'd be x to the 7 minus 2, which is x to the 5th. So we know those exponent rules. Those are the things that we're going to be using here as we're doing some of these problems with rational exponents. The only thing we're changing is we're putting a fraction in the exponent instead of a regular, integer number. So example K, 18 to the 1/2 times 18 to the 7/2 divided by 18 to the 3rd. So we're just throwing it all together here. Order of operations tells us that we're going to do parentheses and exponents first, and then multiplication, division left to right. Well, with this problem, you got multiplication up top, and then it's a big division problem. So we're going to do this part first. So these have the same base. 18 is the base, and so we're going to add the exponents together. It's nice here because the exponents have the same denominator, so that's an easy addition there. 1/2 plus 7/2 would be 18 to the 8/2, which we know 8/2 is actually what? 4. Well, I'm going to write it as 4. And then, that's not x, that's 18 to the 3rd on the bottom. And then the rule for that division is to do what with the exponents? Subtract, so that's going to end up being 18. Again, you could do this with the calculator, but you've got to be careful to put the numerator in parentheses, 18 raised to the 1/2 times, and press the right arrow key, times 18 raised to the 7/2. Press the right arrow key, close the parentheses, divided by parentheses 18 raised to the 3rd. So all of that work to get it typed in there, and gets the same answer out of that, but it's you got to be careful, especially when it's a big fraction looking thing like that. Let's look at this one. 100 to the 3/2 times 16 to the negative 3/4. So a weird one. It's got two different numbers, two different bases, and we need to work that out and try to simplify this as best we can. Okay, so we're going to break down the 100. What multiplies to be 100? 50 and 2. Good start. 50 and would be 2 and 25. 25 would be 5 and 5. So the 100 is 2 squared times 5 squared to the 3/2. And then the 16 we know is 8 times 2, right? 4 and 2, 2 and 2. So it's 2 to the 4th power to the negative 3/4. So I'm just breaking down each individual base here. That's what those numbers are called. And then I'm going to apply the rational exponent. I'm just going to multiply. 3/2 times 2 is going to give me 2 to the 3rd power. 5/2 times, or 5 to the 2nd. Multiply those exponents. That's going to give me 5 to the 3rd power. And then here, multiplying those two together is going to be 2 to the negative 3 power. Now, the bases that are the same, we can put together. 2 to the third, and 2 to the negative 3, what do we do with those exponents? Add them together. They cancel each other out and gives us really 2 to the 0 power times 5 cubed. What's anything to the 0 power? 1. And then we know 5 to the third is 125. So all of that manual work to get 125 as a solution to that. But it's still the idea of working with these exponents is going to come back. We start throwing some variables in it in just a minute. You got to be able to do it by hand. So punching it with calculator is great to check with. But we got to know what we're doing exponent wise to get these where they're coming from with that. All right. So let's look at it with some variables so that we really knock out some stuff here. So let's say we had 4x to the 3/4 times 5x to the 2/5. So the exponents are only on the x's. They're not on the numbers. The 4 and the 5 are just coefficients. They're in front. So since 4 and 5 are the coefficients on front, I'm just going to multiply them together and get 20. And then what's the rule for the x's, the exponents on the x's? They add together because we're multiplying. So we're really adding 3/4 plus 2/5, which would be common denominator to be 20. If you wanted to do that, it'd be 15 over 20 plus 8 over 20. I'm fine with you using a calculator to do that addition. It doesn't matter to me out of that. So 15 and 8 is 23. Again, I'm okay with you using a calculator to add those fractions up if you want to. Just you don't have to put the x in there at all. You're just putting 3/4 plus 2/5. And then to change it back to a fraction, I'm hitting math, enter. And that's how I'm getting the 23 over 20 to get there. And I'm fine with you doing it that way. Let's throw in some division here. 5m to the 4/3 n to the 2/3 squared times m to the 4th over 8n to the 5th to the 1/3. So we're doing a lot of exponent rules here, just kind of throwing a lot at you. But the key is to work each fraction individually first and then put it together. So exponent rule is to multiply this 2 to everything, every exponent. That 5 has an exponent on it. It's a 1. Okay. This 8 has an exponent on it. It's a 1. So you're multiplying this 1/3 to everything there. So I'm working out this first fraction. It's going to be 5 to the 2nd power m to the 8 over 3 over n to the 4 over 3. The second fraction is going to be m to the 4 over 3, 8 to the 1/3, and n to the 5 over 3. And then I'm going to start putting it together out. So I've done the exponent rule. Anything that's on the outside multiplies to every exponent on the inside, always. Okay. So here we're multiplying those together. Got 5 squared, m to the 8 over 3, n to the 4 over 3, and then 1/3 times 4 is 4/3. 1/3 times 1 is 1/3. 1/3 times 5 is 5/3. That's all it did was distribute there. And then I'm going to put it together. So the rules for multiplying fractions are top times top, bottom times bottom. Right? So if I multiply straight across, I know 5 squared is 25. And that's going to be m to the 8 plus 4 is 12 over 3. Then on the bottom, what's 8 to the 1/3? Kind of already done that a little bit. 8 is 4 and 2, right? 8 is 2 to the 3rd power to the 1/3 power, which would be 2. And then we're going to add our exponents on the ends. 4/3 and 5/3 would be 9/3. And then I'm going to simplify those fractions. 25m to the 4th over 2n to the 3rd. That was a little hairy because you got to simplify as you go there. If you don't simplify as you go, it still works out, but it's just anytime you got coefficients mixed in with variables, it makes it a little tougher to do. So you got to be careful of that. Let's do one that's just variables for the most part. It's only got one coefficient, so it's easier to do. Look at the rules again. Oh, y to the 3/7 parentheses y to the 4/7 time, or excuse me, minus 5 y to the 11/7. So just a distributive property problem. It's all this is. So we're distributing the stuff that's in front of the parentheses. We're going to multiply both of these pieces by y to the 3/7. So I'm just going to write out an extra step that I normally would not write. I would usually just do this work. So I'm writing out that extra step where I've taken that piece that was in front and multiplied it to each piece on the inside. Okay. And then I'm just going to do exponent rules for that because the bases are the same here. Y and y, I can add those together. What's 4 plus 3? 7. So that's going to be y to the 7/7 or y to the 1 first power, right? And then this one, we got 3/7 and 11/7, which would be 14/7, which is 2. So we've simplified it just by adding those exponents out of that. Distributive property, anytime you're multiplying, the bases have to be the same, and then you could add your exponents. Always going to work out that way. Whether it's fraction exponents or non-fraction exponents, the same rules. No, there are no new exponent rules that we're dealing with here. We're just dealing with fractions mixed in there is all that's changed about what we're doing in R.6. All right, let's bump over to R.7 and we're gonna do the same thing, but they're gonna change the name of it, and they're gonna call it radical expressions. But what we're gonna do is we're gonna look at them as rational exponents because that's what we just did, what we already know how to do. So we're going to take our radical expressions and think about them as rational exponents. And I'm going to show you how to make that happen. So we'll start with an example, and it's going to be, the instructions will be simplified just like they were in the previous lesson there. So let's simplify the cubed root of 27. And here's how the rational exponents relates to a indexed root. This is the key over here. Whatever n, that's an n right there. Whatever number is right there, and then you're going to have something with an exponent on the inside. The key to this is that can be rewritten like that. You can rewrite a root as a rational exponent or rewrite a rational exponent as a root. Okay, so this one, that 27 has what exponent on it? A 1. So this is really 27 to the 1/3 power. That's what this is showing over here, is what we're doing. It's taking that and rewriting it as a rational exponent, and then doing the same work that we've done in the past. We know that the 27 is 3 and 9, 3 and 3. So that's really 3 to the 3rd power raised to the 1/3 power. We multiply the exponents. We just get 3. So this one has an index of a 4. When I say index, I'm talking about the number that's up here. So anytime you hear or read the word index, that's what it's talking about. So I'm going to put the number 10,000 in there. So that would be 10,000 to what power? 1/4. What do we know about 10,000? It's 10 to what power? Might remember that little trick. Yeah, however how many zeros there are, that's the exponent on the 10. 10 to the 4th power to the 1/4. So that's going to be just plain old 10. The graphing calculator does have an indexed root. I don't think it's very easy to get to, but I mean, it's not too bad. If I wanted to do the cubed root, I can hit the math button, which is right underneath the green alpha button on the left, and it comes up here. It's got a cubed root already programmed in, and then number 5 is the nth root. It's whatever you want to put there. So if you hit number 5, select that. It should give you an empty box there that you could put whatever number you want. Like here, we put the 4, and then press the right arrow key, and then put our 10,000 in there. It should give us the 10 back that we want. So you can get it that way. I actually don't ever use that. I always just change it to a rational exponent and type it in that way because I'm faster at typing it in that way. I guess that's probably the way that I learned it when I was first going through. Probably why I still do it that way. But it either way works just fine as far as checking that goes. Let's try this one. The cubed root of negative 216. That's negative 216 to the 1/3 power. Is it okay to have a negative on the inside of this one?
Yeah.
When is it not okay? Good. When the denominator's even, that's when we got issues. This one, the denominator's an odd number, so no issues to deal with. So we're just going to go ahead and work out the 216. I'm going to break it down. What do y'all know about 216? It's even, right? So 2 goes into it 108 times. And we know a little bit more about 108. Maybe. Yeah, 9 times 12 is how we get that. And then 9 is 3 and 3. And 12 is 3 and 4, 6 and 2. Doesn't really matter which way you go there. So negative 216 is negative 1 times 2 cubed times 3 cubed. I'm going to distribute that 1/3. So I get a negative 1 times 2 times 3 is negative 6 out of that. Again, I'm doing this all by hand. So we see the exponent rules because it's going to help us later on when we start doing things like solving equations with this, working with no numbers, just variables. So it's a key thing to that. All right. So again, you could type that into the calculator. Parentheses negative 216. Close the parentheses, raised to the 1/3 power. Garrett cranks out that answer. You could hit math and then the fourth option and then put in the negative 216 and give you that same result out of that. Those mean the same things. So being able to bounce back and forth between those two things is fairly important. Okay. All right, let's look at a fraction thrown in there underneath a big root, indexed root. So let's just do a cubed root of 125 over 512. I'm going to rewrite it as a rational exponent. And then I'm going to break down those numbers. We've done 125 several times already this evening, so we should know that it is what? Yeah, 5 to the third. 512 we haven't done as much with, so let's break it down a little bit. 2 and 256, because it's even. I don't know much else about it. And then 256 is also even. 2 and 128, which is also even, which is 2 and 64, which is also even. 2 and 32, 2 and 16, 2 and 8. A lot of 2s there. 2 and 4, 2 and 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 2s. 2 to the 9th power. All of that raised to the 1/3. Now, what was the rule about that exponent and those things in parentheses? What does that 1/3 do to everything? Multiplies to every exponent on the inside. So it's going to be 5 to the 3 times a third is 1. 9 times a third. 1/3 of 9 would be 3, right? So it'd be 5 over 2 cubed is 8. Again, can be done with the calculator. I'm not saying shy away from that completely. I'm just trying to work some exponent rules with you, because when we start going into the equations and things, knowing what exponent rules do is going to help you when you don't have a number to deal with, when you got variables to deal with. So that's kind of where I'm at with this. So let's do a little bit of that just rewriting. So we'll write the radical expression for each rational expression. So kind of a different set of directions here. We're not really simplifying. We're taking an expression and writing it in two different forms. Okay, we'll take the form that it's in, write it in the other form. Okay, so what are we on here? E, is that right? So let's take 16 to the 3/4. I know we can simplify that, but we're not working on that right now. We're just working on rewriting that as an index root. What's the index that goes on the root? Be the 4. And then the 16 has what exponent? 3. Believe it or not, they asked that question on the final exam. Questions like that. That's all you have. You don't have to do anything to it. Just rewrite it. Which one of these is the equivalent expression for that? They ask questions like that on the final exam. I hope they ask like 6 of those. They're not going to, but it'd be nice. Let's do x to the 4 fifths. So just a variable. We're just rewriting that as an indexed root. So what's the index on the root? 5 and x to the 4th on the inside. Could it get any easier? No, but it can get harder. Let's make it harder. Let's put a number there. x to 7, x to the 5 over 6. Which one of those has the exponent? X. So that 7 is just hanging out. It's not doing anything as far as the root goes. So the root has what index? And what's on the inside? X to the 5th. Where does that 7 go? In front, because it was in front of the other stuff, right? So the 7 goes out here in the front. That's how that works. Because it's a coefficient. It's a number that's in front of that stuff. So that 7 is going to go in the front. I love how this thing just changes colors randomly. This cable and all, and it just flows in and out. It's like a lava lamp. So, all right, let's do 5x parentheses to the 7 over 8. So this one's a little different. So you got a parentheses with a 7/8 as the exponent. So what's the index on a root? 8. What's on the inside? How do I write it? Do I just put the 7 there? I need to put parentheses around my 5x because that whole thing gets the 7 power. How else could that be written? Good. Yeah, 5 to the 7th, x to the 7th. Both of those are equivalent expressions, meaning the same thing there. Not very likely they're going to work out 5 to the 7th. That's a pretty big number out of that. But all right. Let's go the other direction. So we're going to write as a rational exponent expression. So we're going to start with an indexed root and go the other direction. Later we're on here. So indexed root. Probably a really easy one. 7th root of n to the 3rd. Write it as a rational exponent. N to the what? 3 over 7. Simple thing here. All right. What would this one be? 1/4 power. Good job. What would be another way to write that? Yeah. Split it apart like that. Both of those. This is the first way is probably the most common way, but also that second style is still correct. They're still the same thing. It's just you taking it one step further out of that. Sometimes they do that, especially if that would simplify there, even though 10 to the 1/4 doesn't simplify. If it were like 2 to the 4th power, which is what 16 to the 1/4, that would simplify a little bit, and they would normally do that if it would simplify, but it doesn't doesn't have to happen there. Let's do 15 cube root of x squared. What would this one be? Do we need parentheses? Yes, no, maybe. It's gonna be x to the what? 2/3. Don't necessarily have to have parentheses to separate those. If you put them there, they're not wrong, but you don't have to have them to separate that. It'll work out just fine. Okay. All right. So we're just rewriting there. We're not really doing anything, as far as simplifying goes. We're just rewriting. So let's do a little bit of simplifying, and with these indexed roots, and I want to show you how things work when things actually simplify with that fractional exponent that you get. So if we're going to simplify, what was the issue that we came up with earlier? Yeah, the even denominator caused problems. So when I go to simplify this problem, it's just a variable. So we don't really know what kind of number that is. It's possible that x could be a negative number, right? Because it's a variable. It can be anything. So if we rewrite this as a fraction exponent, that's going to be x to the what? 6/2. But that reduces, doesn't it? To be x to the 3/1 or 3. What we have to add into this problem is absolute value around that. Those are absolute value marks. The reason that we have to add that in there, that even index, the even denominator, and the fact that we don't know what kind of number x is. Only what kind of things does absolute value give us back? Positive numbers only. That's it, right? So that's why putting that absolute value in there makes this work out and simplify the right way. If we don't put the absolute value in there, it doesn't guarantee us that this is a real number and actually works. So that's where anytime that you got an even denominator and it simplifies a little bit, absolute value marks has got to throw in there. Okay, it's got to be there. Okay, let's look at another one, see if it needs it. Very similar problem, just one key difference. So we got the cubed root of x to the 6th. Rewrite that as a rational exponent, be x to the what? 6/3, which reduces to be x to the 2nd power, right? 6 divided by 3 is 2. Now, does this one need absolute values? No, because the denominator on the fraction is what? Odd. And it doesn't matter what happens there. Odd index can deal with the negative. Even index cannot. So this one you do not need absolute value marks on it because the index was odd. That index, or the denominator of the fraction, is what decides whether you need those absolute values or not. Let's say we had this one. This is where we sometimes forget. We get so into this mode of different indices. We forget what one is on that. What's the index on the root here? No. What symbol is that? No. It's a square root, isn't it? That's the square root symbol, is it not? Square root's got a 2 that's understood to be there because it's a square root. Cubed root is 3 there. Fourth root is the 4th power there. Square root's just a 2 right there. They don't ever write it, but we a lot of times will forget that that's supposed to be a 2 right there because we get so used to seeing those other things. So let's rewrite this as fraction exponents. So 81 to the 1/2 power, x to the 8/2, y to the 10/2. What's 81 to the 1/2 power? Or what's the square root of 81 is another way to think about that. 9. What about the x? About the y? Do any of those need absolute value marks? Why does the 9 not need it? Because it's square root of 81, right? So it's a number. It doesn't need that. But what do we know about x? This 4 is even. So no matter what kind of number I put in the place of x, what kind of answer does it get? No, not necessarily even. Positive, right? And what does absolute value do? It always gives us positive back. So if this is already going to be positive, does it need absolute value? No. But what about here? You got y to the 5th power. If I take a negative number and put it in the place of y, say like -2. -2 times -2 times -2, 5 times. That's going to be what? -32. But it can't become an even denominator. Can it be a negative? No, that was the part we had a problem with. So this one is the only one that needs absolute values, is the y. The rest of them don't need it. The x doesn't need it because the 4th power will always be positive anyway. If this had been like x to the 9 over 2 or something like that, then yeah, that's going to need some absolute value marks. But because that worked out to be an even exponent, it's always going to be positive anyway. So you don't have to have the absolute values out of that. So you got to be careful of that. Anytime you simplify that and it ends up with an odd exponent, that's really when you got to have that absolute value in there. Let's say 5th root of m to the 10th n to the 15th. 2 things in there. No number this time. Same idea though. Rewrite it. M to the 10 over 5, n to the 15 over 5. How do they simplify? Do either of those get absolute value marks? Why not? That 5's an odd number. That index is what that's called, or the denominator of the rational exponent is odd. So it doesn't deal with the absolute values. The only time we have to worry about that is if we got an even index that we're dealing with. Even index. Maybe it's a 6th root of x to the 18, y to the 24. Let's kind of drive this idea home here, and then we'll get into a little bit more operational things. Okay. So rewrite it. X to the what? 18 over 6, which is going to be 3rd, and y to the 24 over 6. So x to the 3rd, y to the 4th. Which one of those, or do both of them get the absolute value? Why just the x to the 3rd? Why not the y to the 4th? Yeah, because the 6 was even. The y to the 4th is always going to be positive because it's an even power. Even powers always come back positive. Odd powers don't. So that's where you got to be careful there. All right. Let's do some operations here. Later I'm on. Square root of 5 times the square root of 45. If you remember back from Math 100, you're multiplying square roots together. Been a bit. I haven't done this in quite a while. So we're going to just go over the rules for multiplying square roots together, and then we'll get into the bigger roots, which is what we're doing tonight. So square roots, the rules for multiplying square roots together are outside times outside, inside times inside, always. Okay. So on this one, is there anything on the outside right now? No, there's nothing in front of either of those. So we're just going to multiply those numbers together. So that's going to be the square root of 5 times 45. It's 5 times 45, 225. So we have a square root of 225. I'm going to change that to 225 to the 1/2 power, just to kind of keep it in the vein of what we've been doing. And then I'm going to break down 225. It came from 5 times 45, so I'm going to use that. Pair of threes, so that's 3 squared, 5 squared. Distribute. 3 times 5 is 15. All that work, and the square root of 225 is always 15. But the idea of doing the exponent rules is going to help you as we go through this stuff for the next couple of weeks. Let's throw the variables in there, and that's where it really gets going. 5th root of n cubed times the 5th root of n to the 2nd. Both of those are the same root, which means it's legal to just multiply them together as roots. I tend to go ahead and change them into, since it's variable expressions, I go ahead and change them into fraction exponents. Because to me, that makes it lots easier. Instead of having to deal with bigger numbers on the insides, I can just go ahead and get those. And what's the rule for those two exponents? Add them together. 2/5 and 3/5 would be 5/5 or 1. Just get in. Does it get absolute value marks? No, the index was odd, not even, so we don't have to worry about that. You gotta be careful of those things still coming up. Sixth root of x over y to the 12th. Again, a lot of times when I'm dealing with these roots and it's just got variables in there, I'm going to change it into a fraction exponent just to make it easier on myself. So this is going to be x to the what? 1/6. And y to the, which is actually y squared, right? Now, do either of those get absolute value marks? Why not? Yeah, that's an even index, but it doesn't simplify here. That x to the 1/6 doesn't simplify out to be a nice x to the 3rd power or something like that. So it's not good. That doesn't even get to work. This is still under a 6th root. The y squared, it's got an even exponent on it. So it's always going to turn positive anyway. So it could be written in either of these forms, be able to bounce back and forth between those two. Because that's just the nature of those kind of answers, that you've got to be able to write it in either rational exponent form or in radical form. But they mean the same thing. Okay. All right. So stuff's not hard. Just got to remember your exponent rules. I don't know why I wrote an I. It's T. This is where some folks get a little confused. It looks freaking hard, but it's easy. Okay. Now, how do you eat an elephant? You might know. You might ever eat an elephant. One bite at a time. It's the only way to do it. Okay? So we're going to take one bite at a time. I'm going to start on the bite that's the smallest, the stuff in here. So I'm just going to rewrite that. 17 to what power? 1/4. So I've now taken that and I've gotten rid of one of the radicals in there and made it an exponent problem. But I can do the same thing here. And that looks bad to do it that way. But dividing by 5 is the same thing as taking that thing and raising it to the 1/5 power. And then what's the rule for these exponents? Multiply. So it'd be 1/20. So, and we're not looking to get a decimal equivalent to that, which if you type this in the calculator, that's what it give you, is a decimal for that. And that's not what we're looking for. We're just looking to simplify this thing and try to get it into a rational exponent style of things. Let's do another one of those. I like those. They're fun. Let's do let's do 42 under there. Put a variable in there. So if I start on the inside, what does this become? X to the 42/6, which is actually 7, right? Gotta be careful. Why did I put absolute values on it? Yeah, because it was an even index or an even denominator, and x to the 7th power is not always positive. That's why I put that there. It comes to the 1/2 power. And we just multiply those two exponents together. 7 times 1/2 is 7/2. And I'm just leaving it in the absolute value marks because it's still got to be positive at the end of that because it's got an even index on the root there. Practice is the key to those. Right. There are 2 sections down. We got a couple more to go here. But I think it gets better after that. All right, so we've manipulated some radicals, manipulated some rational exponents. So let's get into solving some equations with this stuff. So this is section, jumping into chapter 1, section 6, and we're going to solve radical equations. Then we'll get into exponential equations as well. Okay, so radical equations. Let's just throw in a problem. Let's just say solve. X minus the square root of 4x plus 12 is equal to 0. Okay. The first thing that you need to do with a radical equation is isolate the radical. and later on we'll talk about the rational exponent part. So we need to get that by itself on one side. So for this problem, I could add the square root of 4x plus 12 to both sides. When I add that to 0, it just gets me the square root of 4x plus 12. And on the left side, those cancel out. It's just x over there. And now I got to get rid of that square root. How do you get rid of a square root? You square both sides. So whatever I do on one side to get rid of that square root, I've got to do the same thing on the other side. So on the left side, I got x squared. On the right side, what happens to the square root and the squared? They go away, and it just leaves me 4x plus 12. Now I have a quadratic equation left. So here's where some of the stuff that we've done in the past comes back up. So we've got to be able to solve this quadratic using some method, either factoring or quadratic formula. Those ways would be nice if we remembered how to do those. But to do either of those, what do I have to have it equal to? 0. So I'm going to subtract 4x from both sides. And I'm going to subtract 12 from both sides so that they cancel out. And now I have x squared minus 4x minus 12 is equal to 0. And I have options to solve that. Okay. I can solve it by factoring. I can solve it by quadratic formula. I'm going to do both methods on this problem just to refresh you on those ways of solving those things. So I'm going to do factoring first. That's that x method thing. Multiply to be 12 and add to be negative 4. Be negative 6 and 2. And that gets you your factors. Set those factors equal to 0 and solve. This is with factoring. Over here and do quadratic formula. Remember quadratic formula? You got x squared minus 4x minus 12 is equal to 0. So we're going to, excuse me, I'm going to set that up. Negative b would be 4 plus or minus negative 4 squared minus 4 times a times c. All that divided by 2a. And simplify that. So that's going to be 4 plus or minus the square root. 16 plus 48 would be 64. And we know the square root of 64 is 8. And I'm going to set up 4 plus 8 divided by 2, 6. 4 minus 8 divided by 2 is negative 2. But I'm not done. I found 2 answers, but I got to check to make sure they're correct because I squared the problem to get the solution there. And anytime I do that, that can introduce extra answers or extraneous solutions out of that. So I've got to check these to make sure that they're correct. So I'm going to go back to the very original problem. That was the original problem. I'm going to plug in my answer and check it to make sure it works out. So I'm going to plug in 6. And the question is, does that equal 0? 24 plus 12 is 36. What's the square root of 36? 6 minus 6 equals 0? Yeah, so that one works. I'm going to check the other one. It is very possible that both of them work, but it's also possible that one works and one doesn't. So that's why we got to check them. All right, so I'm going to plug in -2. -2 minus the the square root of 4 times -2 plus 12. So it's going to be -2 minus square root of 4. Question is, does that equal 0? That's what we're trying to check. What's the square root of 4? -2 minus 2. Does that equal to 0? No, -2 minus 2 would be -4. That does not equal 0. So -2 is an extraneous solution. So it is not an answer. That's extraneous. Extra, N-E-O-U-S. Extraneous solution. Just because it's negative doesn't mean it's automatically an extraneous solution. Just because it's positive doesn't mean it's automatically an answer that works. You've got to just take those answers that you're finding and plug them in to the original problem and check to see if they work. If they do, keep them. If they don't, they're extraneous. That's what you've got to check for here as you're doing these problems. Okay, so that one was a square root problem. Let's look at one that's got a cube root in it. And I put these little tails on the end of my square roots just to show you that that's where that square root ends, so that it doesn't look like I'm putting something else underneath there, or where that root, this cube roots. So I put these little tails on there just to say, hey, that's the end of that particular root. So this one looks a little hairy because it's got 2 roots in it. It's got 2 cube roots in it. But remember, the key is to isolate the root or rational exponent part. There happens to be 2 pieces here. If I add the cube root of x to both sides here, that's going to get them separated so that at least one of them is by itself. And maybe I can get rid of that cube root. So in the same way that I got rid of a square root, I squared both sides, right? So to get rid of a cube root, what am I going to do? Cube it, yeah. Raise it to the 3rd power. That just takes the roots off of and it works out wonderfully on this problem because now I don't have any cube roots in the problem. So by getting the cube roots kind of separated there and isolating one of them, I was able to get rid of both of them with the cubing of each side. And then if it's got an x squared in it, that means I'm going to have to get this equal to 0 and solve it the same way I did the last problem. So I'm going to subtract x. Five x squared minus 13x plus 6. And I'm going to solve that either by factoring or by quadratic formula, whichever way you choose. I'm going to choose factoring on this one. 5 times 6 is 30. Got to add to be -13. Be -10 and -3. I can't use the shortcut on this one because it's got the 5 in front of x squared. So I got to write it out. 5x squared minus 10x minus 3x plus 6. And then group it. Remember doing this not too distant past. My factors are 5x minus 3, x minus 2. Set each of those equal to 0. And solve. 3 over 5 and 2. That doesn't mean that both of them are answers. It doesn't really mean that either of them are answers because I cubed this problem to get it to work. So I've got to go back to the original and check it. So I'm going to go to the original. Cube root of 5 times x squared. And I'm going to plug in one of my x's. I'm going to plug in the 2. And I'm checking to see, does it equal 0? All right. And I'm going to use my calculator to help me a little here. I'm going to say 5 parentheses 2 raised to the third, or excuse me, raised to the second, minus 12 parentheses 2 plus 6. Get that answer. And I'm going to take the cubed root of that. Well, the beautiful part of that is, hey, that's the cube root of 2 minus the cube root of 2. Is that 0? Always, right? Doesn't matter what the decimal for cube root of 2 is. It's that's working. So this one checks. I'm going to keep it. I'm going to do the same thing for the 3 over 5. I'm going to plug it in. So I'm going to hit 5 parentheses 3 over 5 squared minus 12 parentheses 3 over 5 plus 6. Get 0.6. Okay, well, is 0.6 what the cube root of 3 over 5 is? Or, well, what's 0.6 is 3 over 5, isn't it? Yeah. So I've really got the cube root of 3 over 5 minus the cube root of 3 over 5, which is 0. They both check in this problem. So I'm keeping both solutions to this one, not throwing either of them out. Okay? So again, you got to check your answers to make sure that they work or don't work. Okay. Let's do a tough one. Not a hard one yet. Let's do a hard one. Square root of 3x plus 1. So square root's not too bad. But let's put 2 of them in there. And then instead of having it equal to 0, I'm going to have it equal to 1. This is what makes this hard. Okay. What did we do earlier when we had 2 of the roots in it? We got one of them by itself, didn't we? So I'm going to do that. I'm going to get one of these roots by itself. I'm going to get this thing by itself. So I'm going to move the square root of x plus 4 by addition. Okay, so I've added the square root of x plus 4 to both sides. And then I'm going to get rid of that square root that's on the 3x plus 1. How do I get rid of a square root? I square both sides. The issue is on the right-hand side, I'm squaring square root of x plus 4 plus 1, not just the square root of x plus 4. So on the left side, I'm getting 3x plus 1. On the right-hand side, I'm getting the square root of x plus 4 plus 1 times the square root of x plus 4 plus 1. That's what it means to square something, isn't it? Multiply it times itself. Okay, so I'm going to have to square that or multiply that together. So I'm going to do that math. Let's do that math. Let's do square root of x plus 4 times square root of x plus 4. That's just going to be x plus 4. Times 1 would be square root of x plus 4. This times it would be another square root of x plus 4. And then 1 times 1 would be plus 1. Well, I'm going to simplify that right-hand side. It's got a lot of stuff that's the same. You got the 4 and the 1 that can come together. It's going to give me x plus 5. And then there's a 1 in front of each of those. So that's really 2 square root of x plus 4. How many square roots are still in that problem? Can I isolate it? Can I get it by itself? And then square to get rid of it. That's the idea here. So I'm going to move this x by subtraction and this 5 by subtraction. It's going to be 2x plus, or excuse me, 2x minus 4 is equal to 2 square root of x plus 4. Because those are going to cancel out. And how do I get rid of that 2 that's in front right here? This 2 right here. How do I get rid of that? Yeah, if I divide everybody by 2, it'll get rid of it. It's going to be x minus 2 equals the square root of x plus 4. And now I finally have the square root isolated, and I can get rid of it. How do you get rid of a square root? You square. So I'm going to square both sides. Right-hand side, that's just going to be x plus 4. The left-hand side, that's x minus 2 times x minus 2. So this is a hard one. It's really long. None of the math is just crazy difficult. It's just long and a lot of places that you can miss a sign or misadd or mismultiply. So when I multiply x minus 2 times x minus 2, it's x squared minus 4x plus 4. Since it has an x squared in the problem, what do I have to get it equal to? 0. Same old game we've been playing on this whole section. I'm going to subtract 4 as well. So that's going to be x squared minus 5x is equal to 0. That's a pretty easy solve if I remember how to factor. How do I factor that? Take out an x. That's the GCF, right? Remember the GCF way of factoring? X minus 5 is left inside. So I'm going to set them up. X equals 0. X minus 5 is equal to 0. So I got two solutions. I got 0 and positive 5. If I go back to my original problem, I'm just rewriting the original problem there. I'm going to plug these in. So these are nice integers, so I ought to be able to work this out in my head. 3 times 0 is 0. Plus 1 is 1, right? What's the square root of 1? 1. Okay. 0 plus 4. 4. The square root of 4 is 2. This was 1 minus 2 negative 1. Is that right? No. So that gets thrown out. Let's see if the 5 works. It's possible that we did all this work and neither one of those answers works. We'll plug the 5 in. 3 times 5, 15 plus 1, square root of 16. 4. So that's a 4. 5 plus 4, square root of 9. 3. So we got 4 minus 3. Is that 1? Yes. We're going to keep that one. That's our solution. Okay. So that's probably the most difficult that they're going to get on that particular kind. Okay. Don't get any longer than that, really, out of that. Let's look at solving some other roots or equations that have a different way of x to the 3 over 2 is equal to 216. So this doesn't have a square root in it. Doesn't have a cubed root in it. It has a 3 over 2 power. And the shortcut to solving these, number one, isolate the part that has that radical or that rational exponent. Okay. The previous three problems all had square roots in them or radicals or cube roots. This one has a rational exponent. So we're going to isolate that piece. We're lucky on this problem that it's already isolated. We don't have to do that. So we're going to take and then use what's called the reciprocal power. What's a reciprocal? Flip it over. What's a power? Exponent. So we're going to multiply those exponents on each side by the reciprocal that's on the x. What happens when you multiply 3 over 2 times 2 over 3? It turns into what? Which is 1, x to the first power. So it gets us plain old x on the left side. So all I've got to do is simplify 216 to the 2/3 power. 216 raised to the 2/3, 36. Boom. Reciprocal power. This one's short and easy because it didn't have anything else going on with the x. We'll get to some that do. But the idea is reciprocal power. That's really what we were doing with the square roots and the cube roots. The square root, the exponent's of 1/2, and we squared both sides, which is the 2 is the reciprocal of 1/2. For the cube roots, we raised everything to the 3rd power on each side. The cube root is a 1/3 power reciprocal. We're really doing the same thing we've been doing. It just looks different. Let's do a tough one here. X plus 7 to the 2/5 power is equal to 4. All right. So is the part with the rational exponent isolated? Is it on one side? Nothing else over there? Well, we got the x plus 7. It's in parentheses, so it's kind of contained. It's the part that has the rational exponent. The rational exponent is the 2/5. Okay, so it is isolated. So we need to get rid of that. So we're going to use the reciprocal power. What's the reciprocal of 2/5? 5 over 2. It's going to cancel out the exponents on the left side. Give you x plus 7. And then all we got to do is work out 4 to the 5 over 2 power. But here's where we got to be careful. What was the issue that came up on the denominators of the fractions? When did that issue come up? When the denominator was what? Even. Is the denominator of the fraction that I put in there even? Yes. That's where we got to be careful. We've got to use plus or minus. Remember, we had to do plus or minus when we were doing the square roots method for solving quadratics. We do quadratic formula. There's a plus or minus in there. It's all based on that even index or that even denominator on the fraction. So we got to do plus or minus if the denominator is even of the fraction we put in. Not the one that was originally there, the one we put in. Okay, so 4 to the 5 over 2. I'm just going to work that out. 4 raised to the 5 over 2. It's 32. So we really have x plus 7 is equal to plus or minus 32. That means I got two problems. I got x plus 7 equals positive 32. X plus 7 equals negative 32. Subtract 7. 25. Subtract 7. Negative 39. I got to go back to the original problem and check that. So I'm plugging in 25 plus 7. Raise that to the 2/5. I got 4. Negative 39 plus 7. Raise that to the 2/5. I got 4. Both of those worked. Very different numbers. One of them is a pretty big negative. So that both checked, though. I'm still checking my solutions to make sure that they work in the original problem. Always want to check to make sure. Excuse me. All right. So let's look at some exponential functions and equations out of this, which is the same idea. We're going to be doing a lot of the same things in this last section of the evening. Okay, I'm trying to get you out of here at a decent hour before my voice just completely goes away. All right, section 4.2. So we're skipping from chapter 1. We started in the R chapter, 0 chapter of your book, going all the way into chapter 4 tonight. It's really spread out in this book. Exponential functions. Exponential functions look like this. You have a variable in the exponent. Let's just take a basic one to start off with. Anytime we talk about functions in college algebra setting, we talk about the domain. Every exponential function has a domain of all real numbers. Negative infinity to positive infinity, if you're writing it in set notation. Or interval notation. Set notation would be x is the element of the reals. Or all real numbers. Write it out. All the words all real numbers. All of those mean the same things. Okay. Now, excuse me. The range for this is going to be from 0 to infinity. And I'm going to show you why with the graph of that. So I'm going to graph y equals. I'm going to hit the y equals button, clear out some of the stuff. I'm going to type in 4 raised to the x power. Hit graph. This graph hugs against the x-axis down here and then shoots up. You write 4 to a power, 4 to the first power. If x is 1, it's going to be at 4. If x is 2, it's 4 squared. That's going to be at 16. That's a big jump, right? 4 to the third power, 16 times 4 is 64. That's an even bigger jump. So every power of x makes it go higher and higher, faster and faster. So exponential functions grow or decay very quickly out of that. So for this one, our domain is all real numbers because it works. It kind of slows down how fast it moves to the right as it goes, but it's still continuing to move to the right. So the domain keeps going forever. The range starts at 0 and goes up to infinity. It really never gets to 0 because there's no way you can raise 4 to a number and it give you 0 back. If you raise 4 to a negative 10th power, you're going to get a small fraction. It's not quite 0. It's almost 0, but it's not quite 0. So our domain is all real numbers. Our range is from 0 to infinity. Function value for exponential functions, if we had 4 to, or f of 1 would be 4 to the first power, which is 4. If we did f of negative 2, that's 4 to the negative 2 power, which is 1 over 4 squared, which is 1 over 16. So just plugging in the x value is all that is. And if you wanted to do that with the calculator, you could. You could hit trace and negative 2, and you'd get the decimal equivalent for that, which is absolutely fine with me. I mean, you know, fractions are great, but the decimal equivalent is okay too. You could hit trace 1 and get that number. If you want to know 8, you get that. That's a 4 to the 8th power, 65,536. You could get those numbers out of that just by plugging in for x out of that. That's the idea. Okay. Let's look at a decay. So that one's exponential growth because as it moves left to right, it goes up. That's growth. Let's look at the graph of 1/2 to the x. So I'm going to clear that out and just type in parentheses 1/2 raised to the x power. Look at what it does differently. Flips it around, and as it reads left to right, the y values are getting lower and lower. The x values are getting bigger and bigger, but the y values are getting lower and lower. That is what's called an exponential decay problem. Its domain is still negative infinity to positive infinity, all real numbers. The range is still from 0 to infinity. Not changed as far as that goes. The difference is that as it reads left to right, it's getting smaller and smaller. Growth, it's getting bigger and bigger. It's going up. Decay, it's getting smaller and smaller. It's going down. Okay, so that's the difference. And the key difference in those two problems is the base. 4 is a whole number base, so it's going to be growth. A fraction, a small fraction base is going to be decay. That's the difference in the two. So you can tell kind of what's going to be happening based on the number that has the exponent on it out of that. And then you could do function values for that if you wanted to plug in, you know, negative 3 for x. I would just hit trace negative 3. It gives me positive 8 as the value. If they wanted to know what was happening at positive 6, I'd hit trace 6. 0.015625 to the 6th power is actually 64. 0.015625. That's right. Yeah, that's right. But the decimal is fine with me. I'm okay with that. You don't have to get that fraction form out of that. So exponential growth, you got a big number as the base. Exponential decay, you got a small number as the base. Know the difference in those two. Be able to recognize, is this growth or decay? That's most every year I've taught 100, 110. That's been a final exam question. Is this exponential growth or decay? And it's based on just that number that's got the exponent on it. Really easy thing. Okay. All right. Let's look at solving some exponential functions or exponential equations. I like this stuff. This is fun to me. 5 to the x power is equal to 125. So we're solving some equations that have an x in the exponent. The variable is in the exponent here. So this is where knowing those exponent rules that we've been working with all evening comes in, okay? and knowing how to break a number down without, relying so much on the calculator. So what I want to do is look at the number that has the base that has the exponent with the variable in it. And I try to rewrite the other number with that same base. So what do we know about 125? We've used that number quite a bit tonight. That's why I start with it. It's 5 to the third power, right? So this is really 5 to the x is equal to 5 to the third. What does x have to be? It's got to be 3. So if you can rewrite it that way, then it works out to where you have the answer to the exponent. So let's get example there. 3 to the x is equal to 81. What do we know about 81? It's 9 times 9, and 9 is 3 and 3. So 81 is really 3 to the fourth power. So x would have to be 4. So being able to rewrite a number as a certain base. Make it a little tougher. 2 to the 3x is equal to 32. It still goes back to that base. So I'm going to try to rewrite 32 as a 2 to a power. So 32 is 8 and 4, 4 and 2, 2 and 2, 2 and 2. So that's 2 to the 3x is equal to 2 to the 1, 2, 3, 4, 5. Once I've rewritten it with the same base, the equation that I have to do is now 3x is equal to 5. The first two examples, I didn't have an equation that I had to solve because they only had x's on them, right? It was x equals 3. So I didn't have to do anything. I was done. Here it was x equals 4. I didn't have to do anything. X was by itself. On this one, I've got a little bit of work that I've got to do because it's 3x is equal to 5. The bases are the same, so they just go away. So I've got to solve that. How do I solve that? Divide by 3. Real easy. X is 5/3. 3 to the 4x is equal to 243. Okay. Well, I know I can't do anything to a 3, so I'm going to break down to 243. 243, 3 goes into it 81 times. That'd be 9 and 9, 3 and 3. So it's 3 to the 4x is equal to 3 to the 5th. What's the equation that I set up? 4x equals 5 and divide by 4. 5/4. It really is that easy, guys. It's not, not too bad. Let's say we had 3 to the x plus 1. So make the exponent a little tougher. Base still a 3, so it can't get too bad here. And let's make this other side 9 to the x. Oh man, they put x's on both sides. But the key is still rewriting it where you have the same base on each side. Okay, so on the left side, we got a base of a 3. You can't break a 3 down any further. It's already a prime number, right? But 9 can be broken down. It's 3 squared, right? So it multiplies to that x that's there. Now, what's the equation that I set up? Yeah, it's real simple. Subtract x. X is equal to 1. Let's do one where you gotta maybe change both sides. So we got 4 to the x plus 5 is equal to 8 to the x minus 1. What's the relationship between 4 and 8? They're both even, which means what goes into 2. So can I rewrite 4 as a 2 to a power? It's 2 to the what power? Second, and 8 would be 2 to the third, right? So I'm just replacing the 4 with a 2 squared. And I'm replacing the 8 with a 2 cubed. Because you can. And you want the bases to be the same. You can't rewrite 8 as 4 times 2 because then you've got an extra 2 in there. So you've got to rewrite them as the same base. So I'm rewriting them as a base of a 2. Now, what happens with these two exponents here? Multiply together. So that's 2 to the 2x plus 10. What happens with these two exponents? Multiply together. So that's 2 to the 3x minus 3. What's the equation that I set up to solve? Solve that thing. (13) is equal to x. And if you go back to your original problem and you plug 13 in for x up here, 4 to the 18 and 8 to the 12 are the same number. If you work it out. Let's look at another one. We'll do another one of those. We got a few deer in the headlight looks there. So let's try 9 to the x plus 5 is equal to 27 to the x minus 1. We'll make that a 2x minus 1. Sorry. Okay. What is the base that we need to try to get both sides into? Why? Right, that's the prime number that goes into both of them is 3s, right? 9 turns into 3 squared. 27 turns into 3 to the third power cubed. Yeah, 2x minus 1 there. And then we multiply those together. And we set up that equation. 2x plus 10, 6x minus 3. 13 is equal to 4x. Divide by 4. Hey, we got a fraction answer. That's okay. Things don't always work out perfectly. Again, you're going to rewrite the bases to be the same in this particular lesson. Next week, we'll get into some where you don't have the same base to work with and how we deal with that. It involves the logarithm stuff. We'll get into those. All right. A couple more things in this section, just a couple more examples here. And it's basically formula work, plugging into a formula and working from there. And I think this may be probably, of all the things that we do in here, is probably the only thing that maybe you do need to know for outside of math classroom work. Compound interest. That is an R over an N. Yeah, I'm about to try to explain every one of those pieces there. So A is equal to capital P, parentheses 1 plus R over N, close the parentheses, and that's an NT as the exponent. Right? The P represents the principal investment. That means the original deposit into a savings account, that kind of idea, okay? So principal investment is P. That's how much you put into the beginning of the term. The R is your interest rate. If you've got a savings account right now, stinks. The interest rates are very low as far as drawing interest. As far as it's like less than 1%. The N is the number of times compounded in a year, and T is time in years. Okay. Now, the compound interest with most local banks, it's going to be quarterly, which is how many times a year? 4 times a year. Most local banks do that. You can get online and probably find Bank of America or some of those larger banks that are national and get them to do monthly or something like that. But most local banks, it's going to be quarterly just because of the general cost of running their software, having somebody run the numbers every quarter out of that. But it's quarterly is 4 times a year. Monthly would be 12 times a year. Daily, 365. We don't figure in the leap year. Banks don't. They get that money for free on the leap years. And then if they did semi-annually, that's twice a year. Those things. So those are numbers that you're going to put in there. The interest rate is going to be how much they're paying us out. That many times a year. And you convert that to a decimal. Make sure that you're moving your decimal place twice to the left once they give you that. And then the time is always in years. So if they say 6 months, the time's going to be 0.5 years. You're always going to convert your time into years to use this formula. I'll give you this formula for the test and for labs and for final exam. I'll give you the compound interest formula. You don't have to worry about memorizing it. You'll use it enough when we do labs and stuff. You'll have it memorized. It's not that difficult to memorize. Okay, so let's do a little bit of math with compound interest. I always find these eye-opening things to deal with. I don't know what letter we're on here. J, I guess. I got the same alphabet, We invest $2,500 into an account, drawing 6% interest. We have discovered one of those. I don't know if anybody does Dave Ramsey in here, but he always talks about the 12% interest accounts that I can never find. But we can only leave that in there for 2 years. We're going to leave it drawing 6% interest for 2 years, compounded quarterly. How much is the account worth? Okay, so again, we're account worth is just how much is that going to work out to be? So we're going to plug in principal rate compounded n times per year. So we're just plugging in the stuff we know. 2,500 goes in the place of P. The interest rate, 0.06, 4 times a year for 2 years. So we're just plugging in that stuff, cranking out a number, and showing us how much money we earn by just taking $2,500, throwing it in that savings account, and not putting any other money in there with it. We got $3,000 back on taxes this year, so we're putting $2,500 away, and in 2 years, we're gonna have something, maybe make a down payment on a car or something like that. That's what we're trying to do here. Maybe, I don't know what we're doing. Not gonna make enough money, probably do much good there. So I'm just gonna plug that into my calculator, 2,500, parentheses, 1 plus 0.06 divided by 4, close the parentheses, raised to the 4 times 2, I'm just going to go ahead and make that an 8. At the end of 2 years, my account is worth $2,816 and how many cents? 23 cents. Yes, they keep the extra change. You don't get it. That's at 6% interest. Yeah, and there's no way you're going to find an account that's going to give you 6% interest. If you do, please let me know where you found that at, so I can go put my money there, or what little money I have, I'll go put it there, because it's mine. My savings account at my local bank, which is just a holder for money anyway, is like 0.1% right now, just because the interest rates are that low. So you're not going to get that. Now, let's look at the flip side of that. Now, how many people have a credit card? I've got credit cards. You know, you get mailers. Once you start college, it was like an amazing thing that when I started college, you started getting these things offered credit cards. I was like, this is free money. No, so let's do a math problem with that. I always find this so interesting with that. So let's pretend that the credit card company was like a savings account, and we ran up a bill, but it was like a savings account, and we invest. Let's call it that. I'd say first of the semester, had to have some new clothes for school, had to have some books. I ran up a bill, it's $1,500. Not an astronomical amount of money, right? But you know, sometimes $1,500 is might as well be $1 million, right? But $1,500, that's a manageable amount. We could pay that off eventually. But we invest $1,500 at now. What's an interest rate for a credit card?
Isn't it 7.25?
Oh no! If you're getting that, then you got an incredible credit that I've never heard of. It's like 17%. Most people especially if it's your first one. If you've had credit cards before, you can find them that give you a lower rate. But most of them, as college students, they're going to be at like 16.95%. That's like the lowest that you can get. You're probably going to get in the 20% range, most likely. That's the way it was when I was getting through college with that. I've got better ones now, but the first ones really stink as far as interest. They stick it to 16.95%. And let's say we're in college and I'm studying. I don't have time to make payments on this. I don't have the money. I'm trying to make it through. So I haven't made any payments on that at any point there. I'm just putting $1,500, 16.95% interest, compounded daily, because that's how they do it, for 4 years. Okay, $1,500. $1,695 over 365. 4 times 365 is the exponent. We don't pay the minimum payment. We don't pay anything. The interest still accrues. Okay. You make the minimum payment, that pays the interest and keeps it down. But if you don't pay anything, this is what happens. So we're putting that money in there. 1,500. 1 plus 0.1695 divided by 365. Close the parentheses. And I'm not going to do the math. 4 times 365. 4, 365. I'm just typing that in there. In 4 years, I now owe almost twice that. Instead of $1,500, I owe $2,954, and they'll round it up because you're owing them money. So that 0.45 or 44 cents. I always do these kind of problems with my high school students, and they all I have them like write out things they want, like the news PS4, and a game, and a controller, and 50-inch flat screen to put in their dorm room. They think they're going to have these things when they go to college. They ain't happening. And they're like, oh, I just put it on a credit card, and I'm like, okay. And then we do these problems, and they're just like blown away by how much money they will end up owing for something that they're not going to have to keep. But in 4 years, it doubled how much we owed out of that. Now, if you could find a bank that would pay you out 16.95%, that's a pretty good deal. But here, kind of the reverse side. This is not exactly the formula that credit card companies use. They use a little different one. But it's the same idea. It's a rough, general, close estimate to that they can, you don't pay anything on it, you're going to owe twice as much in 4 years. And in 4 years after that, it's not going to be twice as much. It's going to be closer to about 5 or 6 times as much in 8 years. And then it just keeps snowballing. And that's one of the things that we always warn folks about. We're supposed to teach that in high schools now, is personal finance, is warn you about taking the credit card debt and letting it snowball, because it's so easy to do. It's easy, and they prey on young people, unfortunately. Student loans are kind of the same, can get that way too, even though their interest rates are minute compared to that. I teach it to freshmen. Yeah. Yeah, I teach it to freshmen in Algebra 1. Yeah, it's always a good thing. Now, let's take another idea and with this, and I don't know what letter we on here. I skipped the letters. L. All right, let's try to find out if we need a certain amount of money at a certain time. Let's try to figure out how much we need to invest to make that happen. So, how much should I invest to have $15,000 after 10 years in an account that draws 3.5% monthly? Okay, so this problem is a little different. We know how much we want our account to be worth after 10 years. But we know the interest rate on that. So you can find things, if you're willing to lock your money away for a certain amount of time, you can find higher interest rates. CDs, there are some mutual funds that lock your money away for a certain amount of time. They'll give you a higher interest rate out of that because they're going to use your money to make money. So we're going to set this up with our formula for compound interest. We're going to plug in everything that we know. The only thing we don't know is how much we should have put in the account at the beginning. That's the part we don't know. So we know the account worth is 15 grand. We don't know principal, but we know the interest rate, 0.035 over monthly would be 12 times a year, 10 times 12 on the exponent. All of this stuff right here, without the P, is what? What is that in general? It's a what? It's a number, right? So P times this ugly number gets me 15 grand.
So all I gotta do is find out this ugly number and divide 15,000 by it to get there. So it looks like really hard stuff, but it's really just one step equation. You just got a big ugly number to deal with here.
So I'm gonna find that number with my calculator. Parentheses 1 plus 0.035 divided by 12 raised to the 10 times 12. That's that number. I'm going to divide 15,000 divided by that number. To have 15 grand after 10 years, I've got to have $10,575.71 to put in there to begin with. Okay. At that interest rate. $10,575.71. $10,575.71. Notice I rounded up on the cents, because if I rounded down to 70, it would not equal 15,000 at the end. I rounded up on my decimal. Okay. So being able to solve for that is just a division problem, really easy to do. There's one other type of interest that we'll talk about here, and that's continuous interest, which is a very rare one that nobody uses hardly. Continuous interest is not used by a whole lot of banks or anybody, but it is something that is talked about in the college algebra section. Again, I will give you this formula. Continuous interest is a simpler formula. It's principal and then E to the RT. P is your principal. Again, same thing. R is your rate. T is time in years. That's all the same. E is the exponential number, and I'll show you what that is. On the calculator, over here on the left-hand side, look right beside the 4. There's a button that says LN, and above it in blue should be written E to the X power. That's the number we're talking about. E to the first power is about 2.71, something like that. It's just a number that it's kind of like pi. It's used enough that it needed its own little placeholder, so they just used E as the exponential number because that's what came up all the time. So we're going to use that when we go to do this problem here. We'll show you just doing an interest problem with continuous interest. So same idea as before. What is an account worth after 4 years drawing 2.5% interest, continuous interest? On an investment of $1,500. So again, I always call this the PERT formula. That's how I remember it. We're just plugging in everything we know. We know that the principal investment is $1,500. E to the interest rate, 0.025. Time is 4 years. And that's going to get us the account worth. All we got to do is just punch it in the calculator the right way. So I'm going to type 1,500 times, and this is where I got to get the E. So I got to hit second and then that LN button. And that puts the E with an exponent thing there. Okay, and ours was 0.025 times 4. Crank it out. So in 4 years of continuous interest, that means continually, every second, it's dropping the interest back into the account. $1,657.76. That number right? Yeah, 1657.76 is what the account would be worth. Again, continuous interest. Most banks don't use continuous interest. Use quarterly as just a standard, or monthly. Some do semi-annually, depending on what fund you're investing in. But continuous interest, it's just a different formula. It's a different way of calculating. What that does is it takes the compounded interest formula and increases n to infinity. And when you do that, that's how the e gets in there. As you increase n to the 1 plus r over n, as you increase that toward infinity, means it's continually going in there. That's where the e comes in, and it works out for us. Things going on this week. You got Canvas quizzes. Folks, you need to do those. They are grades. If you're not doing those, you're not going to do well. So Canvas quizzes. Next week we'll come in, we'll do labs and lecture over the next set of stuff, which is logarithms and things. So we'll come in and do labs next week. Make sure you're here for those, unless coronavirus hits you, and hopefully it doesn't. And then we'll do lecture, and then we'll talk about the next week, which would be when my school's on spring break and we've got some things going on, so we're not going to meet. But we'll talk about that next week. If you want to work on some problems, I'm going to write them up here for those sections. If you want to work some out of the textbook, I don't know how many of you do that. I think it's helpful. You may not. Canvas quizzes for those 4 sections are available, should be available right now, but you'll be able to work through those.